morning, doctor. Today we are present lab to operational amplifier. We are from Group 1. My name is Jeff Chan Tun Xuan.
My name is Chai Yuan. Now I will present about the introduction. The example of the operational use is LM741. The objective of this lab experiment is to understand basic characteristics of operational amplifier circuit configuration, compare theoretical and experimental simulation in each configuration, and to determine effect of capacitor, bypass resistor, and internal operational amplifier offset voltage to the output voltage. The example of operational amplifier configuration is inverting, non-inverting, summing, differentiator, and integrator amplifier. Now I will pass it to Jeff.
Okay, thank you, Chia. Now I will continue to the data sheet. From the data sheet, the LM741 has an output swing of plus minus 14 volt and a slow rate of 0.5 volt over microseconds. This means if the theoretical output is higher than plus minus 14 volt, the op amps will saturate. And at higher frequency, the slow rate will cause amplitude drop and distortions. These limitations help explain the difference between our theoretical and major result. Next, we will go to the inverting operational amplifier. The inverting amplifier was designed with an theoretical gains of it get from the formula which is shown in the figure. So in the slide, we get is negative 33. So 1 volt is input should produce negative 33 volt. However, we only measure negative 13.961 from the lab experiment. This happened because high gains make the output very large. When the output is large than the plus minus 14 volt limit, the op amp hit the limit and saturate. So the op amps creep near negative 14 volt instead of reaching negative 33 volt. The output is inverted because the input is connected to the inverting terminal, giving a 180 phase shift. This experiment show the theoretical results are net restricted by real op-amp limitations such as output swing and finite gains. In the next experiment, the expect output stay within the voltage limit. So theory and measurements match better. The theoretical output was 11 volt. We get from the formula, and the major output was 11.005, almost identical. This small difference comes from resistor tolerance and measurements accuracy because the output stay within plus minus 14 volt. The LM741s operate in the linear regions, giving accurate amplifications. The positive output outcome confirms the non-inverting behavior. The final experience also stay within the limit. Next, we move to the amplifier, which the value stay within the limit. The theoretical output was negative 6 volt, and we measure negative 0.99 volt, only a 0.01 volt difference. This small error is due to a resistor tolerance and mirror op amps imperfections. Since the output remains within the linear range, the LM741s follow the theory closely. Across all experiments, engineering principles explain the result clearly. The output swing and slew rate explain why the inverting amplifier saturate Wells resistor tolerance and the linear operating regions explain the accurate result in the non-inverting and summing amplifier. By linking this in principle to each outcome, we can see how real op-amp limitations affect circuit performance. Now I will pass it to Chia.
Thank you, Jeff. Now I will continue with the integrated operational amplifier. This is the waveform of the integrated operational amplifier before zoom in. After zoom in, the integrated operational amplifier is like this. The voltage output is calculated using the formula, and we will get negative 1000 watt. And from the waveform, we get the voltage output is negative 998.744 watt. For the integrator, the operational amplifier accumulate the input signal, turning a square wave into a triangular waveform and shifting a sine wave by negative 90 degree. The measured output of negative 998.744 watt closely match the theoretical negative 1000 watt, showing good agreement. The inclusion of the 10 mega ohm resistor is based on the principle controlling DC drift caused by input bias current and small DC offset. Without it, even tiny offset will accumulate, driving the output to saturation. This demonstrates how understanding the operation amplifier non-ideal characteristic guides practical design decision to achieve both functional integration and circuit stability. Next, I will continue with the differentiator amplifier. For the differential operational amplifier, the voltage output is calculated using this formula and get negative 1 watt, and the voltage output value from the graph is 2 watt. The differentiator output of the rate of change of the input signal produce a sharp spike for square wave and a positive 900-degree phase shift for sine wave. The measured output of 2 watt deviate from the theoretical negative 1 watt because differentiators are highly sensitive to noise, varying capacitors, and DC offset. Adding a 100 picofarad input capacitor demonstrates the principle of controlling high frequency gain to limit noise and prevent oscillation. This shows how understanding the relationship between circuit design, frequency response, and real-world non-idealities allow engineers to predict and mitigate unwanted effects in fast response circuit. Now I will pass it to Jeff.
Okay, thank you, Chia. Now I will continue to the conclusions. Uh, Overall, the experiments show that ideal op-amps theory would only in the linear regions once limited by voltage swing, bandwidth, noise, or slew rate. The real LM741's behavior dominate. The highlight the importance of balancing theory with real-world op-amps constraint in analog design. Thank you. That's all for our group.